So I've decided to go ahead and add minerals to the list of topics that we're going to talk about in here. So let me do that. I wanted to really bring you up to speed and everything you learned in Geology 110 in just a few short lectures essentially. So anyway, here it is, and I hope you enjoy it. Thanks. Bye now. Well, this is going to be far short of a comprehensive review of minerals. But we're going to talk about minerals. What is a mineral to begin with? Well, there are 5 parts to the definition, of course. Naturally occurring inorganic solid that has a chemical composition and a crystalline structure. So when we took Geology 110, the Principles of Geology, you learned that things like ice would be considered a mineral because it is naturally occurring. It is inorganic. It wasn't once living. It is a solid. And it has a structure. It's a 6-sided crystal, right? And then we also have a chemical composition, which is H2O. So that was the definition for water. And water, when it's in a frozen state, is actually a mineral. So it's not one that you're going to have to learn, however. So that's kind of nice to know. You learned also in Geology 110 that glass is not a mineral because it is amorph. It is not crystalline, in other words. But in Geology 110, you learned a lot. Okay, so maybe go back and brush up on your notes a little bit, but most of this material you're either going to get in a course in mineralogy that's GLG 332 at Missouri State University, or you're going to pick it up also some of the rock-forming minerals when you take GLG 333, which is petrology. Or you may even see some of them in GLG 334, which is sedimentary geology also. So, just briefly, so what are minerals? You have the 5 points to the definition here. Well, minerals are, by and large, there's about 4,000 of them that are known right now, and it's hovering right around 4,000. So there's give or take maybe a few less than that, or maybe a few more. But that's roughly how many earth materials we have. They're combinations generally of 1 or 2 elements or more. And then, of course, we have those that are the native elements, which would be like sometimes gold, also copper sometimes, and then sometimes silver and a few of the other ones. But we have the native elements, and then we have combinations. And those are usually divided between radicals, which will have a negative charge, and then the positive metal ions of some sort. And so when we say metal ions, we're talking about iron, magnesium, calcium, potassium, all those sorts of things. So we're going to launch right into this. So this is the first mineral here, and when you study these things, actually they're listed in a sheet by their hardness to begin with, but you don't have a way to test the hardness, especially on, unless you have these in front of you. So here is just a short explanation for what these things look like, what they are. This is pyrite. Pyrite has, it forms a crystalline shape that's sometimes 5-sided. They also have things called pyritohedrons, but you'll always see that sort of brassy color, and you'll see sort of like striations on the sides of it. It does scratch glass. It's a really hard metallic mineral. So metallic mineral means that is the description that we use, is it metallic or non-metallic? We're talking about one of the major divisions about how we identify minerals. So this one is metallic. It scratches glass, hardness of 7 or so, something like that. Square-looking sort of minerals, but sometimes 5-sided. It'll leave a black to greenish streak, if you will. They call it fool's gold, of course, and it, of course, is a sulfide as well. Iron sulfide, as you see. And so they use it for quite an astounding number of products, in fact, but primarily in glass. And amber glasses, you will use some very finely powdered pyrite in their mixture. The next sample is an iron mineral, again, but this time an iron oxide, and it's used for the production of iron and blast furnaces and things like that, so they can separate out, or smelters, I should say, separate out the iron from the oxygen. So it is metallic, of course, and sparkles. It's softer than glass, however, glass being around 5.5 in hardness, and it leaves a red-brown streak. It's the one that we can always identify by its streak, and it is a type of iron ore, and this is hematite. We call it specular hematite because it has the sort of like crystal faces on it that will sparkle in light. It's an oxide. And then galena is the next one. It's another sulfide again. Galena is the state mineral of Missouri. Galena has cubic cleavage, so you can see from this that it has 90-degree junctions where those crystalline faces, the planes of weakness essentially, line up with one another. Okay, so it's a lead ore, it's a lead sulfide, it's useful for a lot of things. The lead is anyway, not the galena itself. But it's an important mineral, state mineral in Missouri because of all the mining that we do for it. So the next mineral we have is graphite. It's carbon. Carbon, it's mostly graphite when it comes right down to it, is mostly, as the chemical formula C, it's mostly in metamorphic rocks, as it turns out. So you have to take some sort of organic material, usually, and turn it into graphite. It is metallic. It's considered metallic. It has that greasy sort of feel. It's what we use for pencil leads. They mix it with a little bit of clay and turn it into pencils. Next on the list is sphalerite, another sulfide again, and we have another submetallic sort of mineral here. And it has a yellow-brown streak, 6 directions of cleavage, and you probably wonder, if we only have 3 dimensions, how can you have 6 directions of cleavage? Well, essentially, it's like you can take a cube and then chop it a couple of different ways, to a couple of extra ways. And so that gives you like 6 directions of cleavage. So you'll see a lot of pyramid sort of shapes, if you will, or triangle shapes on this. In this sample, it shows very, very prominently. It's kind of a root beer brown color in this sample, but it's not always that color. So keep that in mind. This is from the Tri-State District of southwestern Missouri here. So sphalerite, an important zinc mineral. In fact, the United States produces a lot of zinc, especially from places like the Brooks Range of Alaska. We have massive deposits of zinc there, up to 85% sphalerite in some of those deposits. I got to work at the Red Dog Mine in the west end of the Brooks Range back, 20 years ago or so, for a short period of time with USGS. And so it's a very important strategic deposit that we have there. So that's sphalerite, ZNS, zinc sulfide. And again, we don't like to smelt these sort of products here because the sulfides will combine with oxygen. And when you combine it with oxygen, that makes sulfuric acid, which is acid rain, and it's not a good substance for the environment. So oftentimes we'll actually export our sphalerite deposits to other countries where those regulations are more lax, although if you wait a few more years, they might be really lax here. So it depends on how things go. Okay, I'm not political in this discussion at all. So that's sphalerite. The next mineral that we have here is chalcopyrite. You'll hear it chalcopyrite sometimes by people who don't know any better. But chalcopyrite is what we generally call it. It's a copper iron sulfate. And it has more of it's metallic, obviously, and it has more of that yellow gold color than what pyrite has. And so, just as the name would suggest, it is related to pyrite, but chalco meaning the addition of that copper. So it's almost an alloy, essentially, included with the sulfite. Okay, the next mineral is magnetite. Magnetite, of course, is magnetic. That's one of the easy properties you can use to distinguish it from other iron-bearing minerals. And so they call it lodestone in some places. It's used as, they use it actually as sometimes in concrete when it comes to nuclear reactors in order to absorb some of the particles that would be emitted from a reactor. And so, but it's also used for an iron ore and a few other sorts of properties that can be used for this as well. So lodestone or magnetite. So the next one is also hematite, and so the next one is an oolitic hematite. It was once a sedimentary rock, and in fact, it may surprise you. You guys have already heard the story about oolites. Oolites or ooids can sometimes be made out of iron. That's usually pretty low in the oceans where that occurs, but it does occur in some sedimentary environments. But they find it, and it is an important mineral in some. In other words, some ore minerals are deposited as sediments rather than being emplaced as hydrothermal or any other type of mineral deposit, if you will. So again, the red-brown streak is going to give this away as being hematite. The next mineral is kind of related to that as well, limonite. Limonite has that sort of rusty color, but it's also can be brownish in color as well. It's going to give a streak, but more of a yellowish brown streak than it will be a reddish brown streak. So limonite is usually a weathering product. You can see here that it's iron hydroxide, and it's been hydrated slightly. So it's essentially rust is what you're looking at. So things like hematite will go to limonite in the rock record. So oftentimes we say after. So it's actually limonite after hematite or limonite after whatever, magnetite or whatever sorts of minerals that you see. This is the most common mineral. In fact, this and hematite are the two most common minerals that people bring in when they think they found a meteorite. And 99.99, oh no, it's 100% of the time when people bring these in, I just, it breaks their hearts, but they're not meteorites, okay? So that is an iron-bearing mineral, but it's not commonly used as an iron ore. Goethite is the next one, and you can see a little bit of limonite on that, the rusty parts on here. Goethite tends to form grape-like clusters. When it forms, it's an oxide with a hydroxide, so it's been hydrated somewhat. It's submetallic here. You may know it also by another name. So if hematite gives you that sort of reddish color, red ochre comes from the weathering of hematite. This yellow ochre, in this case, it comes from the weathering of goethite. And so that is the limonite part of goethite here. So that's kind of the metallic minerals right there. And if we go on, we're really going to talk about rock-forming minerals next, and it all relies on Bowen's reaction series. So Norman Bowen was a genius geologist, and he came up with this idea that there seems to be a systematic way in which silicate minerals crystallize out of a magma. And so he said that there's a discontinuous sort of set of minerals that will occur, and you don't find them with other minerals. So they're going to form first, and then you get the next ones that form, and the next ones form, and so forth. So they're going to form in a discrete sort of manner, in other words. But on the other side, he says there's also a continuous side to this diagram as well, and that happens to be the Plagioclase side. So on the discontinuous side, we have olivine, then pyroxene, then amphibole, and then biotite. And to follow along with this is pretty important, and it describes a lot. Olivine, of course, is a single tetrahedron combined with iron or magnesium or one or the other or both. And so that is a single tetrahedra in its crystalline form. Okay, so it's an SiO4, one of those silica tetrahedron combined with two metallic substances, right? So that's remember we talked about zinc oxide or zircon related to that, sort of like zirconium along with a silicate tetrahedra will give you zircon. And so these minerals, olivine, has that same sort of structure with the SiO4, a 1-to-4 relationship between the silica and the oxygen. For the next one, pyroxenes tend to be single chains. The amphiboles tend to be double chains. And the biotite, as we go down this list, will be, of course, a sheet silicate, okay? So that's how these things form. On the other side, it's completely opposite. It's like they don't form because of any sort of like a polymerization of those silica tetrahedra. Instead, it's all plagioclase on that other side. And so that goes from the dark plagioclase at the very top, that's the anorthite, down to the lightest one, which would be oligoclase. Actually, you can get albite at the other opposite end of that spectrum. And so that goes all the way from mafic into the felsic sort of minerals. And so you can get plagioclase feldspar, even in granites, right? And so, and you can get a biotite granite, pretty common. And you can even get some amphibole sometimes, which will go into a granite as well. The next minerals in this list are K-spar, that is a potassium feldspar of some sort. That would include things like, there's also microcline in there, but potassium feldspar, one of the more common ones. Below that, you get muscovite, and then quartz is the very last thing that will crystallize out of a magma. So in other words, what we're doing is we're lowering the temperature from the very top up here down to the very bottom. So we go from about 1,400 degrees or 1,100 degrees at the top up here, pretty hot, all the way down to 900 degrees Celsius, as I recall here. So yeah, there's the last things that will form then out of a magma. So let's take a look at some of these minerals. So olivine here, of course, is the first one that we have, 6.5 to 7 with the hardness there. The gemstone version of this is called peridot, and that's why we call the rock peridotite that forms out of olivine. It has a lot of different uses. Aluminum casting is one of those. So you can see the chemical formula down here below it. That's iron and magnesium combined with the SiO4. Yeah, if we were to back up into the ratios that you would see in the Bowen's reaction, it's Bowen's reaction series. It's 1 to 4 at the very top. And of course, quartz, the chemical formula is SiO2. And so at the very bottom, of course, it's 1 to 2 then. So you increase that ratio from 1 to 4 to 1 to 2, and you wind up with more pure silica put into that formula, essentially. And so we get a lot of extra things when you're in the upper end of Bowen's reaction series. Pyroxene. So pyroxene is the next group here. And that's the augite, is the variety of pyroxene that we have in our sample kits at Missouri State University. Augite is the next one. So augite is a double chain, has more of a linearity to its structure than what augite has. A lot of people confuse the two of them. Augite tends to be a little bit more blocky in its form, whereas hornblende, the amphibole, tends to be a little bit more linear in shape, if you will. And hornblende tends to be black or dark, whereas the augite tends to have a little bit of green color to it as well. Biotite's the next on the Bowen's reaction series. So with biotite, we're looking at something that has sheet structure, of course, and with the addition of iron and so forth. The chemical formula is long enough. I don't think you need to know it for anything that I'm going to ask you about. You'll probably have to know it for courses like mineralogy and also maybe petrology as well. So remember, these things are all cumulative over the years. On the plagioclase side, we have things that range all the way from Anorthite to Albite. And in between those two end members, we can have Bytownite, we can have Labradorite, Andesine, and then Oligocene, or Oligoclase in those. And then they have a wide range of colors, of course. And Anorthite tends to be sort of black to greenish. And Albite tends to be white in color. So the Anorthite tends to be sodium rich, Na rich, and then calcium rich with the Albite. And we always have 90 degrees of cleavage with this and 2 directions of cleavage. So fracture at the ends of that broken crystal. So what else to tell you about this? That's Labradorite in the picture right here. Labradorite has a property called labradorescence. In fact, it has a sort of purplish color to it. And almost all of the plagioclases, of course, have striations. That's one easy way to tell them apart from potassium feldspars. So the next one's a potassium feldspar. It tends to be pink, and that would include things like orthoclase, microcline, sanidine, and Anorthoclase, so clases, and then also hardness is 6.5 to 7 here. And again, it's the same cleavage. And so I don't know why Oligoclase was mentioned in the last one as well, but if you get a chance, why don't you ask Dr. Michael Felder about that? The next mineral that we have on the list here is muscovite. Muscovite is pretty interesting. You can actually see through it. It has a submetallic luster to it. It is easy to split into flat plates, if you will. So when you find muscovite that's in these large plates like that, it's usually associated with granites and usually a pegmatite, in fact. So that's muscovite in this image right here. And of course, the last mineral is quartz, SiO2, right? It's a silicate, of course. Has a complex three-dimensional structure to it. You notice that we've taken all of in a magma, we will have shredded all of the metal ions out of the magma before we get to this stage. And so quartz has a tendency to not be euhedral. It doesn't form real good crystals or true crystals. Even though it's crystalline substance, it doesn't form really good crystals when it crystallizes out of a magma. It's usually the very last thing that forms. And so when it is the last thing that forms, it just fills in between the mesh and all the other crystals, that sort of mishmash of all those other minerals that we've already talked about in Bowen's reaction series. So quartz is the survivor mineral. If it's the last mineral that forms, it's always also the last mineral that will weather out. And so quartz has a long duration as far as its survivability in the weathering environment. So because it's so dense for one reason. It doesn't have any cleavage planes. It's hard to break it, right? So when you do break it, it has a hardness of 7. And when you do break it, it has conchoidal fracture. That's how we identify it, in fact. When we say vitreous, we're really talking about glassy sort of appearance on those broken surfaces. Some people think that it looks a little bit greasy as well. And so it can be gray in some granites, but it can also be white like you see here, or it can be clear and translucent or transparent. And so you can have all sorts of varieties of this sort of mineral, of course. You can have rose quartz, smoky quartz, and in fact, they even irradiate it to form a gemstone known as, I got to think about this now, citrine. Citrine is irradiated quartz crystals, and so it gives it that sort of yellow color. So sand has a million uses, and not the least amongst them are silicon wafers. So they mix it with graphite, and they melt it, and they form silicon. Silicon is what they use then to make chips. And so it's a semiconductor. Next on the list here, we're going to go back to metamorphic sort of minerals that you commonly find, and that's garnet. And garnet has a really pretty hard aspect to it, 6.5 to 7.5. I don't put the mineral form on here, or the mineral composition, because there's a lot of variety to it. So you can have several different metal cations that can combine with it. It can go anywhere from like a root beer brown color to a dark red color, as you see here. And you can even have green varieties of this, and that's the most common thing that you will see in mineralogy tests, where they try to trick you. They'll give you a green dodecahedron of a particular variety of garnet. So don't be fooled by it. So garnet can also be green. So that is a lot of the silicates. Here's the last, one of the last silicates anyway. Talc has a hardness of 1, and that's why it's included in this list here. It has a soapy feel to it. Most people call it like a soapstone. Soapstones will have either this or some sort of serpentinite sort of material in it, serpentine. And so talc is one of those minerals that they used to use for industrial purposes, talcum powder, for instance. They don't do that anymore because they found out later that it has also an association with it. It will have some asbestos, and so asbestos is not good for people. Just ask anybody who has the kind of cancers that you can get from, what are those late night TV show, the Victim Channel will always have some sort of ads for the carcinogen that this will create through asbestos. So, but talc is one of those hydrated minerals, and that's why it feels so soft. The next mineral on the list then is kaolinite. And kaolinite is kind of like a weathering product of feldspars. And you can see here one of the properties of kaolinite is it will stick to your tongue. It's called hygroscopic, a mineral because of that. So it actually has so much porosity, in fact, that it will actually stick to your tongue. I think there's some connection with Gibbs free energy there if you're taking physics. So there have been articles written about that. But anyway, it'll stick to your tongue. That's kaolinite. That's one of the minerals that will stick to your tongue. There are some other ones out there too. Gypsum is another sort of mineral that's more of a sedimentary rock. Gypsum is a very common evaporite mineral. In other words, it forms in desert sort of environments where you have brines that have a lot of calcium and perhaps sulfate in them. And of course, it's also hydrated. And so there is the .2H2O at the very end of this. So when they make plaster of Paris or they make drywall, they will heat up that gypsum very, very hot temperatures, and it dries off the water that way, and it recombines with water. Then you mix it with water to form plaster of Paris. So gypsum, two varieties shown here: selenite, named of course after the moon, selenite, and then satin spar is the other variety here. Fibrous sort of clusters of crystals here. Next on the list is halite. Halite is NaCl, as you well know. This is the type example we use for ionic bonding because you can break the bonds so easily. So anytime you have salt on your tongue, you're breaking bonds, and you can taste the chlorine then. It's more the chlorine than the sodium that you taste then. It's a halide. Halides are anything in that seventh column in the periodic table. So even the fluorite is going to be considered a halide because of its relationship in the periodic table. So halite and halide makes a lot of sense, and so Cl is on that seventh column. So is fluorine, for that matter. So it tends to be clear and colorless, can be white as well, and if you have small enough crystals of it. Cubic cleavage, again, that's one of the ways we identify it, hardness of 2 to 2.5. Very light specific gravity, 2.17 for its specific gravity. In other words, when you have halite in a sedimentary succession as a deposit, it tends to be fairly mobile because of its low density. And so you can actually form things like salt domes in sedimentary successions because of that. Next on the list is barite. If you look it up in Wikipedia, it's barite with a Y. BaSO4 is the chemical formula. We have a hardness of 4.3 to 5, actually specific gravity 4.3 to 5. And in other words, it's relatively heavy for what it looks like. And so they use that, of course, for drilling muds. You can increase the density of drilling muds, mixing it with bentonite or some other sorts of like essentially kitty litter, and pumping that down into a borehole. It keeps the pore pressures up when drilling oil wells. Orthorhombic system here, and then they have bladed crystals, or they have a fibrous habit very commonly. Sometimes it can be clear. I've seen chunks of barite that are large tabular sort of masses that look a lot like calcite, frankly, which leads us to the next one, segue. Calcite is CaCO3. I have the wrong formula up here right now, but I'll change that before we get into it here. CaCO3, calcium carbonate. Clear, can be white, gray, pink, tan, black. You can have all sorts of colors. Hardness of 3 by definition. It's a carbonate, reacts vigorously with hydrochloric acid. It has 3 directions of cleavage, but not cubic in this sense. It's actually rhombohedral, as is dolomite. Dolomite's our next mineral, and the chemical formula for it is if you just take calcite and add some magnesium to it. Okay, so it's a 2 molar sort of like molecule. So you have to have calcium and magnesium, so it takes 2 CO3s to balance that equation. It could be white, pink, tan. The pink variety tends to form what they call saddle crystals, and so saddle crystals are usually hydrothermal in origin. It could be tan, it could be a root beer brown color. When it's in thin section, very commonly you'll see sort of diamond shapes in sedimentary rocks, and those tend to be dolomite. It can be black as well, as this sample is right here. 3.5 to 4 is the hardness. Again, because it's a carbonate, it's going to react a little bit with dilute hydrochloric acid. Not quite so vigorously as what calcite does, however. Next on the list, fluorite. Fluorite is CaF2, and again, a halite, and it can be clear, white, pink, green, blue, purple, brown, yellow. Yeah, I'm reading off the slide to you here, but hardness of 4 by definition as well. The one thing to remember about fluorite, it's not real common. It's more of a hydrothermal mineral for most situations. You'll find it in sedimentary rocks or sedimentary breccias around intrusions commonly. So commonly it's associated with that sort of hydrothermal sort of activity that you get around intrusions. When you look at the mineral, very commonly you'll see triangular shapes in it, just like as you did with sphalerite as well. If you think about fluorite, you're really looking at 2 pyramids base to base. So it's an octahedral shape. So it's 8 sides. And that's pretty much distinctive for fluorite. That covers pretty much all of the minerals that we have our students in Geology 110, Principles of Geology, study in their lab sets. And so that's just a short review of what you should have already learned in Geology 110. So, and that's going to form the basis for what are rock-forming minerals. And so, both in sedimentary successions, but also igneous rocks. And so igneous rocks tend to be silicates. And so there you have it. So we're going to go on from here. I'm going to actually load this up before the rock review so you can review this first. And even though it was recorded afterwards, because I kind of relented in putting this together. But I think it's just important enough for you to get this. Oftentimes, like for instance, I know that in petrology, it was taught last year in the spring semester. And so we're getting to that sort of like, status of this pandemic where I can't tell exactly what every student has as a prerequisite coming into this course. And so I just wanted to give you some of the review that I could maybe help with, I guess. So anyway, we'll leave it at that, and I will talk to you soon. And we're going to move on with a little bit of review of plate tectonics and things like that, other things that you had in Geology 110. And then we're going to move on to the things that are really important. We're going to start doing our survey then, from the Hadean all the way up to the Holocene. So anyway, I'll talk to you soon. Thanks. Bye now.